These are the notes for section 8.1. This is very much just a review of integration techniques. So one thing you're looking at on this first slide is three different fractions and how to deal with different degrees in the numerator and the denominator. The easiest case is this middle case here because the degree in the denominator is one larger than the degree in the numerator. And so if you let u equal the bigger degree, x squared plus 4, then du takes care of everything in the numerator. So because the degrees are off by 1, you're going to wind up with a du over u, which the antiderivative is the natural log of u, ln x squared plus 4 after you do the substitution. And because x squared is always positive and 4 is always positive, you can get rid of the absolute value bars and just have your final answer in parentheses. Pay attention to the constants. We needed a 2x, so I moved the 25 out front, put a 2x there, which had to be offset with a 1/2. So the 25 moves out front, but the 1/2 offsets the 2 that I needed for the du. The second case on the left here, there's an x squared in the bottom and nothing in the top, x to the 0 on the top. This is a case for inverse tangent. If you move the 25 out front, and if you match up with x becoming u and a becoming 2, then you've got du over u squared plus a squared, which is inverse tangent. So the antiderivative of this is this thing, replacing the a's and the u's with x's and 2's. You get this, and I forgot the plus c, but there it is. So last case, if the degrees in the top and the bottom are the same, or if the top is larger than the bottom, then you're probably going to have to do a quick detour through long division. So you take the numerator, put it inside, put the denominator outside, and then figure out what the long division answer is. 25 times x squared is 25x squared, which will make that disappear, but then 25 times 4 is 100. And then you don't forget that you need to subtract, distributing the negative to both terms. I have a negative 100 here. So now our original fraction is split into two terms, which the antiderivative of those two terms is done separately. The antiderivative of 25 is 25x. Moving 100 out front and taking the antiderivative of dx over x squared plus 4, this is identical to the one we did over here on the left. So now we know that that's inverse tangent of x over 2 with a 1/2 coefficient out front, and doing a little bit of simplifying and cleaning up, you wind up with this statement here. So in chapter 8, since this is the last chapter that deals with integration, you should get some flashcards ready to make sure that you know all these rules inside and out, backwards and forwards. And I'm going to highlight a couple. This first one just says if you have a constant, you can move it out front. Second one, if you take the addition or subtraction of two functions, you can term by term find antiderivatives instead of trying to do the whole thing at once. Jumping down here, the antiderivative of e to the u is e to the u, but if it's a different base than e, don't forget you need this constant coefficient up front, 1 over the natural log of a times a to the u. For your trig functions, the antiderivatives of sine, cosine, and tangent, 2 of the 3 are negative, so the first and the third are negative. For secant and cosecant, these are a little bit more challenging, so flashcards here might be a good idea. And then way down here, your inverse trig functions, you need to just look for patterns. We just did inverse tangent here. If it's constant squared minus variable squared under square root, that's inverse sine. And if you have a variable squared minus constant squared, that's inverse cosine. So flashcards for 18, 19, 20, and some of the trig ones might be a good idea. Okay, last two examples, and each of these are going to be done two different ways, and they're both perfectly valid. This one doesn't quite work initially because if I let u equal 1 plus e to the x, I'm going to need an e to the x dx, which is not upstairs. So to get an e to the x dx upstairs, you can either create one, and the stuff inside the blue shading here is 0, and then separate in two separate questions. So this first one is just 1. The antiderivative of 1 is x. And then this one fits a nice, neat u du substitution. U is 1 plus e to the x, du is e to the x dx. The antiderivative of that is du over u, which is natural log of 1 plus e to the x plus c. Doing it a second way, if I multiply the top and bottom by e to the negative x, okay, e to the negative x times 1 is e to the negative x. E to the negative x times e to the x is e to the 0, which is 1. And then upstairs, 1 times e to the negative x is e to the negative x. And now I have a u substitution where here's u, here's du. It takes care of both the top and the bottom with an extra negative, and I get this answer. So the question is this left one in blue the same as this right one in green? Well, doing some log properties, if I take and undistribute an e to the negative x, or factor out an e to the negative x, I get these two statements. Any Natural log with multiplication can be separated into natural log plus natural log. The natural log of e to the x simplifies into negative x, and again, the absolute value bars aren't necessary because e to the negative x is always positive, and the natural log of e to the something is just the exponent. And I have this statement here, distributing my negative, I wound up with a statement that's exactly the same as the blue one. So initially they don't look the same, but they are in fact the same. And then for the last one, if you forget some of your antiderivative trig functions, it's okay. You should know that the antiderivative of cotangent is the natural log of sine arguments, and with the u substitution, the argument gets taken care of. But if you forget that, you can kind of work your way around that by using trig identities to say cotangent is the same thing as cosine over sine. I'm going to let u equal sine 2x squared, which leaves du as my numerator, 4x cosine 2x squared dx. I need a 4, so I'm going to put a 4 there and offset it with a 1/4 on the outside. And then that's a natural log statement. Replacing my u again, we get the exact same answer as what we had up here. So it's not the end of the world if you forget some of your trig antiderivatives, especially if they are involved with trig identities. And the last screen is another summary that's on page 523. Some of the common patterns are listed over here. I'm highlighting a few of them. Separating the numerator is okay. If I keep x squared plus 1 as the denominator, I can take the two numerators and separate them with a plus. Separating the denominator does not work. So you cannot take 1 over x squared plus 1 and turn it into 1 over x squared plus 1 over 1. That doesn't work. So completing the square and this two-term thing here produces this, which is now set up for one of your inverse trig antiderivatives. And then I guess the rest of them you can read here. They involve just things like trig identities and Pythagorean conjugates, which is again more some trig identities. Okay, that's it for section 8.1, which is a review of integration.